Okay. Good afternoon, everyone. Welcome you all for the NPTEL's problem solving session. We'll start now. All right, we'll start now. Good afternoon, everyone. So, this is a problem solving session for the NPTEL course Fluid and Particle Mechanics. The course code is NOC 25CH49, and we are now in week 7 for the problem solving session, and the session will run from 3 p.m. to 5 p.m. The course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And live session is handled by myself. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, as you all know, the course is a 12 weeks course. The course lectures will be available in the NPTEL website. These are problem solving sessions to help you solve problems in that particular week's assignment. So if you have any doubts, you can ask me. This may or may not include, the particular problem. So you can ask doubt from the previous sessions also if you have any. So we'll start now. As I mentioned, since it is a 12 weeks course, we have week 1 introduction to Navier-Stokes equations and their exact solutions, partially flow, uh, Taylor Quid flow rheology. So since there may be a few ups and downs in the course layout, it was not exactly in that particular week. And week 3 dimensional analysis, turbulent flow, friction losses, Moody's chart, boundary layer theory, introduction to particles, their characterization, particulate phenomena, Brownian motion and forces, motion of particles in a fluid, terminal velocity, particle separation, sedimentation of dilute, concentrated and flocculated dispersions, packed and fluidized beds, filtration. So for books and references, we have Unit Operations of Chemical Engineering, Warren Lee McCabe, Julian Cleveland Smith, Peter Harriet, Fluid Mechanics by Frank M. White, Introduction to Particle Technology by Martin J. Rhodes, and for references, Coulson and Richardson's Chemical Engineering by John Metcalf Coulson, John Francis Richardson, Fluid Mechanics by Piyush K. Kundu, and Principles of Colloid and Surface Chemistry by Paul C. Hemans and R. Rajagopalan. Transport Phenomena by Bert Stewart Lightfoot. So, for before starting the problems, what was covered in week 7 was settling of colloidal aggregates, free settling in multiple particle systems, flow through packed bed, pressure drop through packed bed. I think that's all. Yeah. So what week 7 covered was a settling of colloidal aggregates. In the last week, we saw about settling of a single particle in a medium. So in this particular week, we saw about the settling of a colloidal aggregates, free settling, and later we saw about settling in a multi-particle system. For example, when a single ball is falling in a column, it will settle freely. We call it free settling. And imagine if there are 10 balls in place of a one ball. So in that case, each of the ball will be hindering the movement of the other ball. So it is about settling in multi-particle systems. It will be different from the free settling, and it is known as hindered settling. And finally, it is flow through packed bed and pressure drop through packed bed. So finally, now we will start with the questions for this particular week's sessions. And for question 1, we have: consider an aqueous dispersion of polystyrene particles of 500 nanometer radius. The dispersion is assumed to be dilute such that the viscosity can be assumed to be the same as that of the viscosity of the suspending medium water. The density of particles and that of suspending medium respectively are 1050 kg per meter cube and 1000 kg per meter cube. In order to increase removal of the particles from the dispersion, it is proposed to add salt such the spherical aggregates of 5 micrometer radius are formed. Assume that the aggregates are spherical in shape and particles are randomly packed. Packing density is 0.64 and porosity is 0.36. We have to do the calculation. So we have to calculate the settling velocity of polystyrene particles in micrometer per second. So since this problem is similar to last week problems, I'll give you guys a 1 minute time. Just understand what is asked and try to answer the question. Okay, so what is given in the question? We are mentioned that uh, polystyrene particles whose radius is 500 nanometer and it is dispersed in a water, but the thing is dispersion is very dilute, so that the viscosity of the dispersion is same as that of the suspending medium 0.001, and density of particles is 1050 kg per meter cube, and density of water is 1000 kg per meter cube. In order to remove the particles, they have added a salt and it aggregated. So the aggregate radius is finally 5 micrometer radius, and packing density is 0.64 or porosity is 0.36, either way. Now we have to calculate the settling velocity of polystyrene particles in micrometer per second. So what do? We know that particle diameter is twice the radius, which is 2 times of 500 nanometer, and it is 2 into 500 nanometer. So it is 1000 into 10 power minus 9 meter. So it is 10 power minus 6 meter. Now for particle density we have it is 1050 kg per meter cube, And for fluid density, we have 1000 kg per meter cube. And fluid viscosity is 0.001 pascal second. And packing fraction is 0.64. Now to find, we have to find the settling velocity in micrometers second. Again, unit is very important here. And formula, we know it is a Vt. Now we are assuming it as free settling and we are calculating settling velocity. Vt is equal to gdp square into rho p minus rho f by 18 mu. And now we are substituting it. Vt equal to 1050 minus 1000. 1050 minus 1000 into 9.81 into 1 into 10 power minus 6, that is dp to the whole square, divided by 18 into 1 into 10 power minus 3. So when we do that, what are we getting? We are getting 2.725 into 10 power minus 8 meter. Okay, 2.725 it is. And in micrometer, that will become, so we have 2.02725 micrometer per second. Oh, it is meter per second. So since it is given that the solution is dilute enough, we are just calculating the free settling. Here we are not calculating the terminal settling velocity. I mean heated settling velocity. So we are just calculating the free settling. So the formula, as we all know, is g dp square into rho p minus rho f by 18 mu, where dp is the diameter of particle, rho p is the density of particle, rho f is the density of fluid, mu is the viscosity of the fluid. So substituting everything, we were getting answer as 2.75 to 10 power minus 8 meter per second. But in the question, it was clearly mentioned that we should give the answer in micrometer per second. So we are converting it into micrometers. So it is 0.02725 micrometer per second. So that is for question 1 solution. Now we will go on to question 2. One more announcement: if at any point of time my internet connection breaks, please wait for 5 minutes. Here today we are having slight instability in the internet connection, so if you can wait, I'll try to join back in some time through my mobile data. So question 2, the number of particles in the spherical aggregate. So in the question it was mentioned that it will form an aggregate. So now we are asked what will be the number of particles in the spherical aggregate. So what I'll give you a hint and I'll give you guys time. So please use that time for solving. So what we need to do, we need to find the number of particles in the spherical aggregate. So number of individual particles we need to find in that is forming a spherical aggregate. So we know the diameter of the aggregate and also we know the diameter of the what do we call diameter of the individual particles. So if we calculate the diameter of volume of the individual particle multiplied by the diameter number of particles, so we are multiplying the number of particles that will give us the volume of that will give us the volume of individual particle into number of particle will give us the volume of aggregate uh, into its packing fraction. So I hope it is clear. So that is how we will do. So as mentioned, I'll give you a 1 minute time. So try to calculate and give me the answer. Okay, we'll see the answer now. Okay, we'll see the answer now. So first, what is given? Radius of the individual particle is given, that is 500 nanometer, or 500 into 10 power minus 9, which is 5 into 10 power minus 7 meters. And radius of the spherical aggregate is 5 micrometers, which is 5 into 10 power minus 6 meters. Now we will find the volume of particles in dispersion. Sorry. Polystyrene particles that are, or let us be volume of polystyrene particles. So volume of particles, polystyrene particles is pi by 6 dp cube. So again d. So volume of polystyrene particles, since it is a spherical particle, it is pi by 6 dp cube. Okay, something, sorry, it is not 5, should be, it should, yeah, okay. So volume of polystyrene particles, as I mentioned, it is pi by 6 dp cube, or pi by 6, so it is not, I mean it is 2 into 5. Or we can, what we can do is, I just calculated it wrong, but it don't affect the solution, but anyways we will change it now. Diameter of polystyrene particles in dispersion is 2 into 500 nanometer, or 1000 nanometer, and it is 1 into 10 power minus 6. Now radius of spherical aggregate is 5 micrometers. Now again we will calculate the diameter of spherical aggregates. diameter of spherical aggregate, that is 2 into 5 micrometer, 2 into 5 micrometer, and it is 10 into 10 power minus 6, or this 1 into 10 power minus 7 meter. So volume of polystyrene particles is pi by 6 d polystyrene particle, diameter of polystyrene particle cube, pi by 6 dp cube. So here we need to now change it. It is 1 into 10 power minus 6. So it is 3.14 divided by 6 into 10 power minus 18. So answer is, it is 5.2333 into 10 power minus 19. So it is minus 19. Okay. Ten power minus 19. So now volume of spherical aggregate is pi by 6 diameter of aggregate cube, and maybe I can like put it here. Diameter of polystyrene particle is d polystyrene, and it is d aggregate, and volume of aggregate d aggregate cube. Again this is different. 1 into 10 power minus 7. So again this will become 5.2333 into it is 10 power 3.14 divided by 6 into 10 power minus 21. So it will be minus 22. So number of spheres in aggregate will be equal to packing density. So I'll show you how. Okay, this is so this is volume of aggregate, and this will be like volume of individual particles, individual spherical particles. So volume of aggregates into, okay, volume of individual particles, number of, sorry, I think I did a small issue here. Again it is sorry, here it is slightly wrong. It is 5.233 into 10 power minus 19, or else divided by 33 minus 22. Actually, it should be other way around. Just give me a minute. I'll just check once. Oh, sorry. Here it is. I did wrong here. 6 and this is 19. It is 22 and it should be like polystyrene particles. That's what I was. I don't know. Sorry for the confusion. Now it makes sense actually. Volume of aggregates. Aggregate. I'll explain now. It will make a better sense. So radius of polystyrene particles is given. We calculated the diameter of polystyrene particles, and radius of aggregates and diameter of aggregates is given. So we calculated the volume of polystyrene particles and volume of the aggregate by using the formula pi by 6 dp cube. So actually, when all this, let us consider this is the volume of a single particle, and this particle makes up the polystyrene aggregate. So this aggregate has one volume. So this is volume of aggregate. So the aggregate volume, the volume of particle, single particle into number of particles uh, will give us volume of aggregate into packing density. So that is the formula. So because how it is, because so it is like the aggregate is composed of individual particles, but it is not fully covered with particles, so it has a certain volume density, certain packing density. So aggregate, volume of aggregate into the packing density will give us the volume of individual particle into number of spheres in the aggregate. So number of spheres in aggregate is equal to volume of aggregate by volume of polystyrene particles into packing density. So that is how we get the solution. So and volume of aggregate is 5.2233 into 10 power minus 19 divided by 5.233 into 10 power minus 22 into 0.64. So this gives us 1000, and 1000 into 0.64 is equal to 640. So the number of spheres in aggregate is 640. So now let us move to next solution, next question. If there, I hope there is no doubt. So, okay. I'll go to next question. If there is any doubt, please let me know. So here we just calculated the volume of individual spheres and volume of aggregate. So volume of individual spheres into number of particles will give us volume of aggregate into packing density. That is how we got the solution. Now we will go to question 3. In question 3 it is given that settling velocity of the spherical aggregate in micrometer second. So for that we are asked to find the settling velocity of the spherical aggregate. In the previous question we found the settling velocity of the individual particle. Now we are asked to find the spherical aggregate, and for that we need density of the aggregate. So I'll show you how to do that. So particle diameter is 5 micron. Just a minute, I'll just cross check once. 10 into minus 5. it is minus 6, it is minus 5. So it doesn't matter, only here it changes power. So it will be minus 19 and here it will be minus 16. I'll put it here. So yeah, sorry for the confusion. It was slightly calculation went wrong, but anyways, now it is clear. I hope everything is clear now. Number of spheres equal to 640. So settling velocity of the spherical aggregate in micrometer per second. So what we should do is particle diameter is 5 micrometers, so it is sorry 2 times of 5 micrometer. So it is 10 into 10 power minus 6 or 10 power minus 5 meter. Density is 1050 kg per meter cube and fluid density is 1000 kg per meter cube and fluid viscosity is 0.001 pascal second and packing fraction is 0.64 and we need to find the settling velocity of the aggregate. So in the previous question, the first question what was asked? Settling velocity of polystyrene particles. Now we are finding the settling velocity of the aggregates. Again in micrometer per second only. So be consistent with the unit because since these are cases where you are giving the answers by typing, it will give a wrong values if you give in a different units, because if it is a multiple choice questions you will be aware of what unit it is, because answer mismatch you will get to know. But since it is like most of the questions are like where you need to give the numbers, please be careful while you are giving the answers. So now we need to find the Vt in equal to rho p minus rho f into g into dp square by 18 mu. Here instead of p we should use aggregate. So formula for rho aggregate is rho p into 1 minus epsilon plus rho l into epsilon. So now first let us find rho aggregate. Rho aggregate is equal to rho p, that is 1050 into 1 minus 0.36. So epsilon is 0.36. A symbol We can insert epsilon. Oops. Was it given? Packing fraction is 1 minus epsilon is 0.64. So now 1 minus epsilon is 0.64. Epsilon will be equal to 1 minus point equal to 1 minus 0.64 equal to 0.36. So now we are substituting everything back in the formula, and it is 1050 into 1 minus 0.36 plus 1000 into 0.36. So what will give us 1000 into 0.36 plus 1000. Okay, when did it become? Sorry, it is 1050. Okay, 1050 into 0.64. That gives us 1032, and the unit is kg per meter cube. Now we are finding the velocity of the aggregates, settling velocity of the aggregates. So Vt is equal to rho aggregate 1032 minus rho L, that is 1000, into 9.81 into diameter of aggregate, that is 5 micrometers. So it is 10 power minus 5 meters. So 10 power minus 5 to the square by 18 into 10 power minus 3. So if we calculate, what are we getting? 1000 into 9.81 divided by 18 into 10 power minus 10 by minus 7 to 10 power minus 7. So it is 1.744. It is not 744 into 10 power minus 6 meter, or directly 1.744 micrometer per second. So again, we are calculating the settling velocity of the aggregate. So from apart from the normal calculation, what differs is that we have to calculate the density of the aggregate. So in the settling velocity formula, we use rho p minus rho f into g into dp square by 18 mu. So instead of rho p, we use rho aggregate, and rho aggregate we calculate it using density of particle and density of liquid, and by means of the packing fraction formula. And after calculating rho aggregate, we substitute back in the terminal settling formula, and we get the solution. So that is how we do this particular question. So I hope question 3 is clear. So settling velocity of aggregate in micrometer per second. I hope it is clear. Now we will go to question 4. Question 4. Terminal velocity of a particle settling under hindered settling condition is dash when compared to the terminal settling velocity for an isolated particle, that is free settling. Option A equal, option B lower, option C higher, option D higher or lower, option E equal or lower, option F higher or equal, option G all of the above. So in the question, we are asked to compare the terminal velocity of a particle settling under hindered settling velocity, and compare it with the free settling velocity. So since it is a theory question, I'll give you I'll give you a 1 minute time. Please check. Please think, we will discuss the answer. Okay, so when we talk about terminal settling velocity, we know that when a particle is falling freely in a liquid, it moves faster compared to when it is moving in a hindered manner. For example, consider this example wherein there is a room full of people and in another room there is only one person. So in both the cases there is the same exit, same door. So if we want to move that, if that person wants to move in room where there is no one else, he can move it faster. But whereas if he wants to move out of the room in the same uh, yeah, like in the room where there are many persons, his movement will be slowed down by the other persons. So what I mean to say is, okay, let us consider it like this. So there are two rooms. In one room it is empty. In another room there is a room full of people. So in both the rooms, in first room we want to go out, and if we want to go out, we can easily go out because since there is no one else apart from us. Consider the second case where we have to go out again, but our movement will be blocked by so many other people. So our speed will be reduced. So second case is the hindered settling condition, and first case is the free settling or the free settling condition. So now we can say that terminal velocity of a particle under hindered settling is slower when compared to the velocity for an isolated particle. So it is option B, lower is the right answer. So the similar room case is what we have to apply it under the larger case. So I think it is like when we allow a particle to settle in a single medium, it will be it can settle fast, whereas when it is settling under the hindered settling condition, it will be slow. So answer is option B, lower is the right answer. Now we'll go to question 5. In question 5 it is asked that the pressure drop per unit length for flow of a fluid through a pipe filled with packing when compared to the flow of same fluid through a cylindrical pipe, assuming same flow velocity calculated based on cross-sectional area of the pipe is always dash. The pressure drop per unit length for a flow of fluid through a pipe when it is filled with packing, when it is compared to the flow of same fluid through the cylindrical pipe of the same cross-sectional area, assuming same flow velocity calculated based on the cross-sectional area of the pipe is always dash. So we are now asked to compare what will be the pressure drop per unit length for same flow conditions when one is filled with packing, other is not filled with packing. So again I'll give you guys a minute time, so just take it to analyze the situation and we can discuss. So I'll give you the option first. Option A, lower. Option B, higher. Option C, higher or lower. Option D, equal. Option E, equal or lower. Option F, higher or equal. Option G, all of the above. So answer is option B, higher. So why, we will see it. Flow through a plain cylindrical pipe follows the Hagen-Poiseuille law for laminar flow, or Darcy equation for the more generalized equation. Flow through a packed bed is described by the Ergun equation, which accounts for the viscous losses, inertial losses, and porosity. The pressure drop depends on the resistance to flow. Packing, when we have a packing, it introduces tortuosity and obstructions to the flow, and because of that, flow moves through a narrow complex paths between the particles, thereby increasing the pressure drop. Then porosity is less than 1, so effective flow area is actually reduced. So this increases the friction and energy dissipation even if the superficial velocity flow per area is the same in both the cases. Pressure drop per unit length for flow through packed bed is always higher than for flow through an open pipe of the same cross-sectional area and at the same superficial velocity. What is saying? So flow through a plain cylindrical pipe follows the Hagen-Poiseuille law, and flow through the or Darcy-Weisbach equation, and flow through packed bed we normally use the Ergun equation. So when we are talking about flow through a packed bed, we have losses accounting from viscous losses or inertial losses or porosity, and pressure drop actually depends on the resistance to flow. So when we are talking about pressure drop, it depends on the resistance to flow, and the packing offers actually obstructions to the flow, and fluid moves through the narrow complex paths because the additional material causes the effective flow area to be less, and it increases the friction or energy dissipation even if the velocity is same in the both the cases. So because of these reasons, pressure drop per unit length for flow through packed bed is always higher than for flow through open pipe of the same cross-sectional area and at the same superficial gas velocity or superficial liquid velocity. So now we'll go to question 6 actually. Certain type of particles of density 3000 kg per meter cube are settling under the force of gravity in an organic liquid which has a density of 1500 kg per meter cube. The viscosity of organic liquid is 1 cp. Radius of the particles is 0.05 mm and volume fraction of particles in organic liquid is 0.2. Assume Stokes settling and the exponent n to be equal to 4.1. Report your answer in meter per second. Calculate free settling velocity. So what is given in the question? We are mentioned that a certain type of particle whose density is 3000 kg per meter cube is settling under the force of gravity in a liquid which has a density of 1500 kg per meter cube, and the viscosity of that particular liquid is 1 centipoise. 1 centipoise is equal to 0.001 Pascal second. And radius of the particles is 0.05 mm, or it is 5 into 10 power minus 5 mm. Sorry, 5 into 10 power minus 5 meter, and its radius is 2 times of that, which is 1 micrometer. Sorry, 10 power minus 4 meter. And volume fraction of the particles in the organic liquid is 0.2, and we are asked to assume Stokes settling and exponent n is 4.1. So now first question, we are asked to calculate the free settling velocity. So since we by now we know the free settling velocity, I'll give you again 1 minute time. So just calculate the answer and we will discuss the calculate the answer. We'll discuss what exact values after a minute. So we'll see the solution now. So what is given? We are given the particle radius is 0.05 mm and particle diameter is 0.1 mm. So it is 1 into 10 power minus 4 meter, and density of particle is 3000 kg per meter cube, and fluid density is 1500 kg per meter cube, and fluid viscosity is 1 centipoise or 0.001 pascal second, and we need to find the settling velocity, free settling velocity, that is important. Now we'll use the formula, and it is Vt is equal to rho p minus rho f into g into dp square by 18 mu, and rho p is 3000, rho f is 1500 into 9.81 into 1 into 10 power minus 4 the square divided by 18 into 1 into 10 power minus 3. So what value we are getting? 1500 into 9.81 into 10 power minus 8 divided by 18 divided by 10 power minus 3. So it is 8.175 into 10 power minus 3 meter. It should be meter per second actually. Eight point 175 into 10 power minus 3 meter per second. But in the question, what was asked? It was asked to, okay, meter per second. So it is same. So it is okay. 0.0082 meter per second. Settling velocity equal to 0.0082 meter per second. So this is question 6. Now for question 7 we have, in the analysis of fluid flow through a packed bed, the actual fluid velocity in the void spaces between particles, that is interstitial velocity V dash, differs from the superficial velocity V naught, which is based on the total cross-sectional area. Considering this, which of the following statements are correct? Interstitial velocity increases proportionally with the superficial velocity V naught. Interstitial velocity decreases as the superficial velocity increases. Interstitial velocity decreases as the porosity of the bed increases, and interstitial velocity decreases as the porosity of the bed increases. So I'll give you again 1 minute time because theory question only. So we'll discuss the answer after that. After this question, we'll take a 5 minutes break. Okay, so we'll first discuss each of the options one by one. So first one is interstitial velocity increases proportionally with superficial velocity. This is true. Interstitial velocity is directly proportional to the superficial velocity. So option A is true. That is V bar is equal to V naught by void fraction. And interstitial velocity decreases as the superficial velocity increases. So this is false. And third one, interstitial velocity decreases as the porosity of the bed increases. So again this is false because it is inversely proportional. And finally, interstitial velocity decreases as the porosity of the bed increases. This is true. So answer is option A and D. So answer, interstitial velocity V bar increases proportionally with the superficial velocity V naught, and interstitial velocity decreases as the porosity of the bed increases. So that is the answer. So yeah, I want symbol. I want to change this to a normal epsilon. So small epsilon, and that is for here. So yeah, time is 4:1. We'll start back by 4:05. I'll keep question 8. Mm, yeah, I'll keep question 8. We'll discuss the answer after we come back. Okay. Okay, we'll start again. Oh, sorry. I think we'll start now. If Vs is the superficial velocity or the empty tower velocity, and V is the average velocity of the fluid flowing through the packed bed, what is the relation between superficial velocity and the average velocity of the fluid? So as we all know, Vs is the superficial velocity, and V bar is the average velocity. So V bar will be average velocity will be Vs by that fraction. So V bar will be greater than Vs because we are dividing Vs by the void fraction in the bed, and that gives us the average flow velocity of the fluid. So V bar will always be greater than Vs. So how V bar is V greater than Vs? Vs is the superficial or the empty tower velocity. The velocity calculated assuming the entire cross-sectional area of the bed is available for flow. That is as if no packing is present. That is why it is also called as empty tower velocity. And V bar is the interstitial velocity or average velocity through the actual voids. The real velocity of the fluid as it moves through the void spaces in the packing. Okay. So Vs is, I mean, real velocity is always greater than the superficial or the empty tower velocity. Now we will go to question 9. A packed bed is constructed by considering a cylindrical column of 800 centimeters square cross-sectional area and filling it with solid spherical particles of density 3.5 gram per centimeter cube up to a bed height of 1 meter. The mass of solids in the bed is 40 kg and diameter of the particles is 1 mm. And calculate the voidage of the bed. A packed bed is constructed by considering a cylindrical column of cross-sectional area 800 centimeters square and with spherical particles whose density is 3.5 gram per centimeter cube, and we filled the particles up to a height of 1 meter. The mass of the packing is 40 kg and diameter of the particles is 1 mm. So now we have to calculate the voidage of the bed. So just take a minute and find out the answer. I'll give the answer in a minute time. So how to do? Now we are asked to calculate the voidage. What is voidage? It is the void space, empty space in the bed. So voidage is volume fraction occupied by the voids. So it is just we have to calculate. What is the fraction? It is just we are saying this percentage is occupied by the solids. The rest of the percentage is empty. So that we need to know what percentage or what fraction is empty. So that is what is asked in the question. How do we calculate? So given the column dimensions, we can calculate the volume of the column or volume of the cylindrical column. So now we know the total volume. Now next we need to find the volume occupied by the particles. So if we know the volume occupied by the particles, we can calculate the volume occupied by the voids, that is the empty column wall, empty space in the column. So that gives us the void volume. So that volume divided by the column volume will give us the void fraction. That is how we need to do. So we will move towards an solution. So first, what is given? A packed bed cross section of cross sectional area 800 centimeter per centimeter square and density of solid spherical particles. So how do we calculate the volume of solids? We are given the density of the solid particles, and we know the mass of the particles. So mass by density gives us the volume, and packing height is 1 meter, and mass of solids in the bed is 40 kg, and diameter of particles is 1 mm, and diameter of particles is 1 mm, and we need to find the voidage, volume fraction occupied by voids of the bed. So what do? We calculate 800 centimeter square, we are writing in meter square, so 800 into 10 power minus 4 meter square, and density of solid spherical particles equal to 3.5 gram per centimeter square. Packed bed cross sectional area is 800 centimeter square. Alright, packing height is 1 meter. Now what we need to do? Formula, and we'll give the solution. So formula is straightforward. As I mentioned, it is void fraction is equal to volume of voids in the bed divided by the volume of the bed, or it is equal to 1 minus volume of solids in the bed divided by volume of the bed. And volume of the bed, okay, let this be here. We'll put that in solution. First, we need to find the volume of the bed. So volume of the bed is equal to cross sectional area into bed height. So if volume, so what is the volume of the bed? It is the cross sectional area into that height, gives us the volume in 3 dimension. Area is in 2 dimensional, and height in multiplying both gives us the volume. Like equation, text, and this is also text. Volume of the bed is equal to cross sectional area into bed height. So cross sectional area is 800 into 10 power minus 4 into bed height is 1 meter. So that gives us 8 into 10 power minus 2 meter cube, or 0.08 meter cube. And volume of solids in the bed is again it is a text. Volume of solids in the bed is equal to mass of solids in the bed by density of the solids, and volume of solids in the bed is therefore equal to 40 kg by 3500 kg per meter cube. So in the question it was given 40 kg, and we know the mass of density of the solids, which is 3500. So we divide both and we will get the volume of solids in the bed in meter cube. So 40 divided by 3500 gives us 0.0114 meter cube. So now we know the volume of the bed and we know the volume of solids in the bed. So what can we do? Void fraction is equal to 1 minus volume of solids in the bed divided by volume of the bed. So it is 0.0114 divided by 0.08 gives us the volume fraction of particles in the bed, that is 0.1429. Okay, it is 29 actually, 285 or 29, and 1 minus this gives us 0.8571. Slight change, but void fraction is therefore 0.8571. What does this tell about our bed condition, that void fraction is 0.8571? Okay. The thing is, this is some unrealistic values. Imagine that 85% of the bed is unoccupied by the particles. So in reality, it don't exist like this. So this occurred because I changed the values to give you a different question compared to what your assignment is. So because of that, it came into some uh, unrealistic values, and since I didn't have time, I didn't check, uh, go back and do the changes again. So but the concept is this, but it is unrealistically high. But anyway, this for a calculation purpose it works. So now we'll go to question 10. Calculate the hindered settling velocity of the particle with specifications in the previous problem, but with diameter of the particle 0.1 mm in the fluid medium of water. But with diameter of particle, the particle dp equal to 0.1 mm. So in the previous question, what was asked? A packed bed is constructed by considering a cylindrical column of 800 centimeter square cross-sectional area and filling it with spherical particles whose density is this and up to a height of 1 meter, and mass of solids in the bed is 40 kg and diameter of particle is 1 mm. And we were asked to find the void fraction. So in this particular question, what has changed? Diameter of the particle is changed to 0.1 mm, and we are given a new fluid medium, and that is water. So now packed bed cross sectional area is 800 centimeter square, which remains unchanged. So it is 800 into 10 power minus 4 meter square. Density of solid spherical particles is actually 3.5 gram per centimeter cube. So it is 3500 kg per meter cube. Packing height is 1 meter. Mass of solids in the bed is 40 kg and diameter of particles is equal to 1 mm. So now we changed this alone. Diameter of particle is 1.1 mm, or it is 1 into into 10 power minus 4 meter. Okay, everything else is there. And fluid density is 1000 kg per meter cube, and fluid viscosity is 0.001 pascal second. And we have to find the hindered settling velocity of the particle. Are we clear till here? Now we will go to finding the hindered settling velocity. So what we know is, we know the free settling velocity as rho p minus rho f into g into dp square by 18 mu. And from the free settling velocity, we can calculate the hindered settling velocity as free settling is equal to hindered settling into 1 minus epsilon to the power of n. So that is how we calculate the hindered settling velocity. So accordingly, now we will substitute the free settling formula, and it is 1000 rho p is 3500 minus 1000 rho f into 9.81 into 10 power minus 4 divided by 18 into 10 power minus 3. So it is 2500 into 9.81 divided by 18, and we will get 10 power minus 5. So it is the 0.0136. We can put 3136. We'll stop at 4 digits, meter per second. Here also it is meter per second. It is just because I copied from, one single slide I made and made changes for the further problems. So that's why everywhere it is meters, not because of anything else. So now what we have to do, we have to find the hindered settling velocity, because we have found out the value for the true settling velocity. Sorry, free settling velocity. So hindered settling velocity is equal to V naught into 1 minus epsilon to the power of n. And here we know epsilon. Uh, we know epsilon. Uh, okay, here we'll write, okay, void fraction equal to, what did we find out? What did we find out? 0.8571, 0.8571, which is a quite high value, but we will write here. %, is filled with voids is not realistic one, but anyways, for our case, let it be. So 0.0136 meter per second. And for finding n, we need to calculate the Reynolds number. So Reynolds number is rho v dp by mu. So rho is 1000 and it was 0.0136. Okay. 1000 into 0.0136 into 10 power minus 4 divided by 0.001. It is 1.36. 1.36. And from literature, if REP is less than 0.2, it is n is this, and 1 to 10 it is this, 10 to 100 it is this. So we can take, like 4.4 n, and since I'll clearly mention, okay, I'll clearly mention that values will be unrealistic in some cases, because like it was changed by myself. Please don't bother with that, let it be. So okay, packing fraction, why do we need to calculate again? This is not required. Okay, this we should have done in the last slide itself, no? Okay, okay, we are just going step by step, nothing else. Everything is zoomed out. It is looking very odd. 800 into 10 power minus 4 minus 4, 8 into 10 power minus 2, it is just like to calculate that again, not anything else. Okay, basically we are not using that, so let it be. But yeah, the solution is, first we are finding n, and later we are according to the formula, v naught is this and vh is this. So we found out v naught initially, and we have to find the hindered settling velocity. And hindered settling velocity, we know v naught, we have to find epsilon, and we have to find n. So we found v naught first, and we found n next, and now we have to find the epsilon. So it is It's not a formula, but yeah, again it is not a solution. So volume of bed is similar to what we saw last problem. So I am not going to repeat it, but void fraction is volume of voids in the bed divided by the total volume of the bed. And we know the total volume of bed is equal to cross-sectional area of the bed into the bed height, packing height. And volume of voids will be like subtracted from the volume of solids. So volume of solids is masked by particle density, so that gives us the volume of solids. So put together we will get a very high void fraction value, or void fraction is equal to epsilon. Okay, so now we have to find the hindered settling velocity. Hindered settling velocity calculation. So hindered settling velocity is equal to Vh is equal to V naught into 1 minus epsilon power n. So that is equal to V naught is 0.01362 136, and epsilon is 0.1425, not 1425 actually, 0.1429. So 1 minus 0.8571, let it be like that, 1 minus 0.8571. So answer will change slightly because of that, to the power of 4.14. 1 minus 0.8571, 0136, it is 2.6 into 10 power minus 6, 6042 into 10 power minus 6 meter per second. So that is the hindered settling velocity. So, or else what else we can do? We can change numbers in the question actually. So I'll give you one more numerical actually. Mm, what we can do is we'll delete it actually. What we can do is dp we can reduce it, and mu we will increase. Okay, dp we will reduce it some more, 0.05 mm. Okay, so here it is 0.05 mm and it is 5 into 10 power minus 5 meter. Now what happens? 5 into 10 power minus 5, 5 into 10 power minus 5. So in that case what happens? 2500 into 9.81 into 5 into 10 power minus 5 into 5 into 10 power minus 5 divided by 18 divided by 10 power minus 3. So it is, I'll go straight away, 1.09 into 10 power minus 6 meter per second. Something is wrong, something is wrong. I'll do again 2500, sorry, 1500 into 9.81 into 25 divided by 18, 10 power minus 10 plus 3 minus 7, power minus 7. So it is, okay, 5, okay, it is 3.4063 into 10 power minus 3 meter per second. So actually what we are doing is, since it is kind of clumsy values, we are just changing it, nothing else. And from this we'll remove this. Rho V dp, rho is 1000, V what did we calculate? It is 3.4063 into 10 power minus 3. Oh, why this is going like this? I don't know. Power minus 3. Okay. And dp is 5 into 10 power minus 5. Again, values are actually going so low. But anyways, 5 into 10 power minus 5 into 1000 divided by 0.001. It is 0.17, or again it is low, but yeah, since I wanted to show exactly in Newton's regime, last time it was coming slightly in you know Stokes regime, so that's why I'm changing it. It is 4.6 now. I mean, last time it was coming slightly in Newton's regime. I want it to come in Stokes regime. That's why I'm changing it. So we are just changing the numbers and doing the calculation again. We are not doing anything new. We are just changing the diameter of the particle to half of its initial diameter. So initially it was 0.1 mm. Now it is 0.05 mm, and rest of the calculation remains the same. Just the values are changing. Now it is this remains the same. We are not going to touch it actually. So V naught is actually, what did we get? It is 3.4063 into 10 power minus 3. So V naught is 3.4063 into 10 power minus 3 into 1 minus 0.8571 into 4 point, I mean to the power of 4.6. I'm just maintaining what was taught in the class so that it will be useful, you know. That's why I changed the numbers. It is just the procedure, nothing else matters. So 3.4063 into 10 power minus 3. So answer is 4.4201 into 10 power minus 7 meter per second. So what was the unit in which the question was asked? Calculate hindered settling velocity. So it is 4.4201 into 10 power minus 7 meter per second. So if we compare, hindered settling velocity is very much lower than the free settling velocity that we are able to observe from this particular problem. So that is for question 10. Now we will go to question 11. Calculate the equivalent channel diameter for the flow of fluid through this packed bed. Report your answer in micrometer. So we are asked to now find the equivalent channel diameter DEQ for the flow through this particular packed bed, and we are asked to find give the answer in micrometers. So we will do that now. So equivalent channel diameter is given by formula to find the equivalent channel diameter. D equivalent is equal to 4 into epsilon by AS. Now what is unknown? AS is unknown. Specific surface area is unknown, and it is equal to 6 into 1 minus epsilon divided by dp. That is surface area divided by the volume of the particle. So it is 6 into 1 minus epsilon divided by dp. So dp again here it varies. So what was that? What was the diameter? Diameter of the particle is dp is equal to 0.05 mm or 0.005 centimeter. So 6 into 1 minus epsilon. So 6 into point, again got changed now, 0.8571 divided by 0.05. So 1 minus 0.8571 into 6 divided by 0.005. 171.48 centimeter square by centimeter cube. So now we have to substitute it in the original equivalent channel diameter formula, and we will get 0.8571 divided by this particular value. So it is 171.48 into 4. That will give us 0.019, okay, or else we can take 0.02 centimeter. Now in the question it was asked to report to the answer in micrometer. So what we have to do, we have to multiply by minus 4, 10 power minus 4, and divide by 10 power minus 4, so that we can get 1 for unit, and the rest will go for the conversion. So it becomes 199, or it is 200 micrometer, 0.02 centimeter or 200 micrometer. So that is how we calculate the equivalent channel diameter. Alright, I hope it is clear now. If you have any doubts, please ask at the end of the session, or we can discuss in the next week as well. I feel like I am going to and fro in some cases, but if you feel so, let me know. Okay. An aggregate consisting of particles of density rho p is settling in a liquid of density rho l. Assume the porosity of the aggregate to be epsilon. Density of the aggregate, rho aggregate, can be approximated as dash. So we already dealt with a similar problem, in the previous case. So there it was rho aggregate is equal to rho p into 1 minus epsilon plus rho l into epsilon. So this is particle density into volume fraction of particles, and liquid density into volume fraction of liquid. So that is a thing. So it is a very simple question. Now we will go to question 13. And we have 3 more problem. Any problem? Okay. All are theory questions only. So yeah, we can go ahead. The particle terminal settling velocity, okay. The terminal settling velocity of a particle, terminal settling velocity of a particle is dash than that of the terminal settling velocity of aggregate consisting of these particles. Option A same, option B lesser, option C greater, Option D, none of the above. So what is asked is, we are calculating the terminal settling velocity of a particle, and we are calculating the terminal settling velocity of the aggregate consisting of these particles. So which will be the individual particle terminal settling velocity will be lower or same or greater is the question. So before answering this, actually we did a similar problem. So why can't we go and check there, so we will get a practical understanding of how it works. So this is the free settling velocity, 0.0082 meter per second of a single particle. I hope that is the question I am talking about. Yeah. But organic liquid aggregate, no, not this one. Yeah, this one, not this one as well. Okay, this problem. First problem which we talked in today's class is asked to find the aggregate, and firstly we asked to find the settling velocity of the polystyrene particles. So settling velocity of the polystyrene particles in micrometer per second is 0.02725 micrometer per second. Whereas the same when made into the aggregate, what were we getting? What was the settling velocity? 1.744 into 10 power minus 6 meter per second, or 1.744 micrometer second. So we can see that aggregate terminal settling velocity is actually higher than the individual terminal settling velocity. Here it is 1.744, and there it was some point something, right? 0.02725 micrometer per second. We can show here. But yeah, 0.0273, and here it is 1.74. So aggregate terminal settling velocity is considerably higher than the individual particle terminal settling velocity. So keeping that in mind, let us answer the question 12 or 13. So aggregate terminal settling velocity is higher than the individual particle terminal settling velocity, or in other words, individual particle terminal settling velocity is lower than that of the terminal settling velocity of the aggregate consisting of these particles. Even though the density of aggregate is lower than the density of individual particle, the aggregate settles faster. So answer is option B, lesser, because we are comparing individual particle with that of the aggregate, so it is lesser. Option B is the right answer. Option B, it is not A. So when we are talking about explanation, the terminal settling velocity of a single particle is generally lesser than the terminal settling velocity of an aggregate made up of those particles. Aggregates consist of multiple smaller particles clumped together, creating a larger effective size and different drag characteristics. Experimental studies show that aggregates such as fractal or loosely bound clusters can settle 2 to 20 times faster than predicted for single solid particles of equivalent mass, largely due to structural properties like lower relative density but much larger size. Relative density is lower, right, but size is larger, and reduced drag per overall cross-sectional area for aggregates. As a result, the settling velocity of an aggregate usually exceeds that of a solitary particle of the same material, since aggregates moves more rapidly through the fluid under the gravity. So that is for question 13. Now let us go to question 14. The concept of fractal dimension is widely used to characterize colloidal aggregates. For a three-dimensional aggregate, which of the following is correct? Option A, df is equal to 2. Option B, df is less than 2. Option C, df is equal to 3. Option D, df is less than 3 by 2. Option E, none of the above. So as we all know that df, I mean I have shown you the answer, right? So you people know the right answer is none of the above. So my question is not regards to the right answer. So my question is, which is the right answer if none of these are right? I mean, what is the correct answer if none of these are right? That is my question. So answer is none of the above, that we all know by now. So option E, none of the above is the right answer. So if none of the above is the answer, which is the correct solution? So I think for a minute and we will discuss. Okay, answer is actually df is less than 3 is the right answer. The fractal dimension df is a measure of how dense or compact a structure is, particularly when it is irregular or self-similar like colloidal aggregates. It quantifies how the mass of the aggregate scales with its radius, that is mr is proportional to r to the power of df, where mr is the mass of aggregate within radius r and df is the fractal dimension. For a 3D system, if the structure is fully dense or solid, df is equal to 3. But if it is a loose or porous aggregate, df is less than 3. So that is the case. What we can do, what we can do. So that is for question 14. Now we'll go to last question for today's session. So today's last question deals with uh, question 15. In a system of charge stabilized particles, the total interaction potential as a function of separation distance phi r is given by the sum of attractive phi r, phi attractive r and repulsive r interactions. The repulsive interaction in such a colloidal system arise due to option A, surface charge on the particles, option B, van der Waals force, option C, depletion effects, option D, bridging. So answer is, I mentioned here clearly, it is surface charge on the particle. So why is the question? We'll discuss it. So in a charge stabilized colloidal system, the total interacting potential between particles is often modeled as phi r is equal to phi repulsive r plus phi attractive r, which is given in the question itself, where phi repulsive r arises from electrostatic repulsion due to surface charge and electric double layer. Phi attractive R arises from van der Waals force, which are always present due to induced dipole interactions. The stability of such colloids is primarily explained by the electrostatic repulsion between similarly charged particle surfaces. As outlined in the DLVO theory, this electrostatic repulsion results from the presence of like charges on the particle surface, which generate repulsive Coulomb force, preventing aggregation at short separations. So, what is it saying? In a charge stabilized colloidal systems, the total interaction potential phi r is given by phi attractive r and phi repulsive r. So phi attractive R arises from the van der Waals forces which are always present due to dipole-induced dipole interactions, and phi repulsive R arises from electrostatic repulsion due to the surface charges and electric double layer. So when we are talking about repulsion, it is because presence of like charges on the particle surfaces, and that results in a repulsive Coulomb force that prevents the aggregation at the short separations, and attraction is due to the van der Waals forces. So that is for explanation for attraction and repulsive forces. So in the question it is asked that repulsive interaction in such a colloidal system arise due to surface charge on the particle. So that is for question 15, and that's all for today's session. If there are any doubts, we can discuss, or I'll give you a quick recap of what we saw, and we can see. Okay, in today's class, what we saw is settling of colloidal aggregates and hindered settling and flow through packed bed. So mostly, I rather than going through problems, I'll give you a quick recap. So colloidal aggregates, when we are talking about colloidal aggregates, it is composed of a multiple individual particles, and it has a certain packing fraction. It is not entirely composed of particles, but rather some voids are also there. So based on that, what conclusion we can draw? We can say that the colloidal aggregates settle faster than the individual particles. Because of this property, they are used in various separation processes and all. Because the aggregates settle faster, we make the particles to aggregate and let them settle. So that is the concept with colloidal aggregates. And second one is, when we are talking about aggregates, its density differs, and its density is given by particle density into particle fraction plus void density, liquid density into liquid fraction or something else. And using this aggregate density only, we need to calculate the settling velocity. And second is the multi-particle system. So if it is a free falling system, we experience a higher velocity compared to when it is moving in a multiple particle system, because hindered settling will be occurring, and hindered settling reduces the movement of the particle, and therefore Vh is equal to V naught into 1 minus epsilon to the power of n. So its velocity, free settling velocity, is basically reduced in the hindered settling velocity values. In terms of values I am talking about. Next is flow through packed bed. So in that, what concepts we have seen? We have seen flow through a packed bed, and we saw superficial gas velocity and average velocity. So we saw average velocity is greater than superficial velocity. Superficial velocity is the empty column velocity. And also we saw how pressure drop in a packed bed is higher than the pressure drop in a normal empty column. So we saw about how to calculate the void fraction. Void fraction is nothing but volume of voids divided by the volume of bed. So volume of voids, how will we know? We don't exactly know. So we can calculate void fraction as 1 minus solid volume fraction. So solid volume fraction we can get as solid volume by total bed volume. Void volume also, it is like absence of particles by the total bed volume. So anything is fine. So that we use in different approaches. So these are the things we learned in today's class. If there is any doubts, please let me know, or else we can close the session. All right. We'll close today's session. Thank you for attending today's session, and we'll meet again next week at the same time, Saturday 3 p.m. to 5 p.m. Thank you.